Hello everyone, my name is Kamil Zajkowski.
Hi, my name is Arif Amzad.
And I'm Alex Petukhov, and together we are Team 4 LP-PPG. Our chip is a low-power analog front end for photoplethysmographic heart rate detection. In our approach, we identified that the optical transceiver in a standard PPG front end consumes an order of magnitude more power than the downstream processing blocks. Thus, we sought to develop a front end with more involved signal processing that allows for an aggressive reduction in transceiver energy. To do this, we designed two signal chains, one low-frequency benchmark and a high-frequency experimental chain that borrows synchronous detection techniques from radio front ends. As we show, this improves our SNR and decouples received signal strength from the emitter duty cycle. Hello, welcome to the demo video for LP-PPG. My name is Alex, and we're going to be walking you through today how our chip operates on the test board. So first of all, you'll notice that we have two oscilloscopes and one power supply over there, and there's a couple things I want to highlight here. First of all, this is us running at our initial baseline state, and you can see that the current draw is a continuous 2.1 to 2.2 milliamps. This is going to change as we progress through the demo. So directing you over here, we have a couple of oscilloscopes with a couple of signals. This here is what I call our high frequency signals of interest, and on the right, we have our low frequency signals of interest. What we have in the high frequency range are three signals that are important to our chip. In yellow, we have the clock that is produced by the LED driver. This is not relevant in the current mode of operation, but will become relevant in a little bit. In green, we have the actual signal that we are sending to the LED. This can be changed by control potentiometers on our board. And lastly, in blue, we have the high frequency signal coming out of our mixer, which is not on right now, so you're not seeing anything. On the low frequency side, you'll see a series of readings of Kamil's heart. In yellow, we have the actual signal coming into our initial filter. You'll notice that it's quite faint, it has some DC component, and you can't even really see the pulsatility, although maybe on those really large motion swings you can see it a little bit. But more importantly, in green, we have our analog out. I'll have to apologize for the inconsistency here in our readings, but it is dependent a lot on the mechanical contact between the finger and our current probe. But it is what it is. In any case, you can see our analog output, and in blue is the 1-bit digital signal that is encoding the heart rate in the rising edge of that square wave. We're not getting great readings right now. We're using our LF chain, which has not great sensitivity, but we're going to make it worse. So the first thing I'm going to do here is control the duty cycle of our LED. Why this is significant is because the LED is the dominant source of energy consumption on our chip. In fact, the chip burns around 7 milliamps when every block is firing. Oops, wrong way. Okay, so as I turn this pot, you'll see on our high frequency chain that the signal over feeding the LED is getting reduced. The duty cycle we can pull down from 100% a DC signal down to a 50% square wave, for example. And now, after this settles, you'll see that we're still getting readings, but the amplitude, let some motion artifact settle, but the amplitude is reduced, and our digital conversion gets even worse than it was before. And now I'm going to keep cutting this. We're going to go way down to 10% duty cycle. I'm just going to check myself right here. Oh, right on the money. So, a couple things. First of all, you'll see that our amplitude of our signal is even further reduced. Ignore the motion artifact. Sorry, wait for it to settle down for a second. We have significantly reduced signal. We're not able to accurately capture it as a digital signal. But on the upside, our power consumption is way down. We've gone from 21 to 4 milliamps. Of course, our LF chain is a baseline implementation, and we have our experimental HF chain that performs better under these circumstances. So I'm going to switch us over to that real quick by flipping this. And now you see a few things. First of all, over here in the high frequency domain, we're still sending this very small duty cycled signal, but our mixer now has this output. What's happening with our mixer is that the baseband signal is getting mixed up to 1 kilohertz, and our initial 1 kilohertz frequency domain copies of our PPG signal, when those two are convolved at the point of the transmitter, is getting brought back down to baseband. So we're basically swapping some stuff around the frequency domain and pulling down a copy of our signal that is decoupled from the influence of duty cycle. And indeed, what you'll see here is that at the output of our stages, we get a much stronger heart signal when the motion artifacts die down than we were before. And as a matter of fact, at 10% duty cycle on our HF chain, we're now running better than we were at 100% energy on our LF chain. But why stop here? Let's keep cutting. All right, and I'm just going to cut power now from 10 down until we're running 3 milliamps of continuous current. And you can see that we are still reading, actually at a comparable level to what we were reading at 100% power on our LF chain, but we're burning about 10% of the overall power. For the sake of posterity, I'm just going to take a second to explain everything that happens after our chip. So you can see that we extract our signal as a 1-bit digital trail. And specifically, I mentioned that we encode heart rate as the rising edge, which is true. We use an Arduino to sample the digital output of our chip and run a very basic queue structure wherein we wait for a rising edge, record the time that it is received, convert that to beats per minute, and feed that into a FIFO structure. This FIFO structure is then averaged out, and we get our average heart rate. We could employ more advanced digital signal processing to, for example, anticipate common sources of motion error, or to produce a slower changing signal with respect to time, or even if we had a bit more RAM and time on our hands, some like Kalman filtering to produce a very accurate estimate. But ultimately, this is what we have going for our demo today, and it is at least comparable to this off-the-shelf component here.
Here we are comparing our sensor to a commercial PPG sensor. As you can see, our sensor is able to capture the BPM closely to the commercial sensor, with ours being slightly slower to react due to a larger Q in our filter.
So looking at the system overview, I'll start with the block diagram on the right. We begin with the LED driver, which produces a PWM signal with a controllable duty cycle, which drives the infrared photodiode. So with a finger placed over the photodiode photoreceiver pair, light will reflect through the finger, which the photoreceiver can detect, and produce an initial PPG signal. Amplification can then go through 2 possible signal chains, either a low frequency, baseband chain, or a high frequency chain. The baseband serves more as a benchmark or a plan B in case things go horribly wrong, while the high frequency chain is more of our intended application, designed for 1 kHz, and is a much more efficient application with a much lower 1/f noise, and thus an improved overall SNR. After HF amplification through the TIA, a mixer then downconverts the signal back to baseband. Afterwards, a Mossberg-Ackerberg bandpass filter is used to isolate the signal from various noise sources, such as 1/f noise, any motion artifacts, or 60 Hz ambient light in the room. With the signal isolated, it's then amplified through programmable gain amplifier stages, allowing us to tune the gain as our signal changes with duty cycle. Finally, a comparator serves as a 1-bit A to D converter, allowing us to have a digital output at the end of our signal chain. It's implemented with hysteresis, which combats any 1/f noise that's amplified through our signal chain and then shows up at the output. Running through the system goals, we wanted a 95% heart rate detection accuracy compared to a commercially available device, and our goal was under 5 milliwatts of power consumption in our design for the analog front end, which is everything excluding the LED driver. We also required that our system would be operational with both a continuous input and a 50% duty cycle of our LED. For our targets, we wanted to get our duty cycle down to just 10%, and we wanted a wearable footprint, meaning that the photodiode and photoreceiver would be something that can easily be worn on the finger or at the wrist, similar to commercially available devices. For our reach goals, we wanted to find the minimum duty cycle at which our entire system would still be operational, and at this duty cycle we would have minimum power consumption. At the very least, we wanted our total system power, the analog front end and the photodiode total, to be under 10 milliwatts.
Now we will begin to talk about the schematic design. Let's begin with the LED driver, which is responsible for transmitting a variable pulse width high frequency signal to an LED. To create the variable pulse width to drive the LED, a relaxation oscillator was employed to create a triangle wave between two reference voltages. Starting from the left, the circuit has a on-chip resistor divider to create the two reference voltages. The block to the right of the resistor divider is a current mirror, which is used to charge and discharge a capacitor to create a triangle voltage. Depending on the capacitor's value and the reference current on the current mirror, the frequency of the LED driver would change. This current mirror also has additional switches to pump additional current into the capacitor in case we wanted to go to a higher frequency. Moving to the right are two comparators, a PMOS for the low voltage reference and an NMOS for the high voltage reference. These comparators feed into an SR latch, which is responsible for charging and discharging the capacitor. On the bottom is a hysteretic comparator that feeds into a driver inverter. The voltage on the triangle wave is compared to the reference voltage being inputted into the hysteretic comparator, such that as you increase the reference voltage, the duty cycle increases, giving us a range of 5% duty cycle to 100% duty cycle. This duty cycle signal is then amplified by the driver inverter, which features a low R-on resistance to supply an adequate amount of current that finally drives the LED. Shown in these plots are the LED driver signals as a function of time for the minimum duty cycle on the left, a 50% duty cycle in the middle, and a high duty cycle shown on the right. The reference voltages generated by the on-chip resistor divider are shown by V high of 2 volts shown in red and V low of 0.5 volts shown in orange. The triangle wave is the voltage on the capacitor shown in blue, and the reference voltage for the comparator is shown in green. As shown by these plots, as you raise the reference voltage, the duty cycle of the output to the LED, shown in purple, increases. The analog front end begins with the transimpedance amplifier, or TIA for short. This amplifier was designed to convert and amplify the photodiode current into a voltage for the rest of the analog front end to process into a heart rate. The TIA was designed in the FF corner as it gives the lowest phase margin across BVT, with a TIA spec being 60 degrees of phase margin and 60 degrees of loop gain. Since the TIA was at the front end of the signal chain, the TIA also required a low noise spec while maintaining a power budget of 200 microamps. One challenge of designing this TIA was the filter's input impedance reduced the overall open loop gain, which affected the overall linearity. To combat this drop in open loop gain, the power of the second stage was increased to drive the output. Overall, the TIA was able to accomplish these specs for the given power budget.
The mixer was utilized in our high-frequency chain to improve the SNR in this alternative signal path. This was achieved by upmixing the original received signal at baseband to some higher harmonic where it would get filtered out by the subsequent filter stages, and downmixing higher frequency reflections of the system to baseband, which were surrounded by decreased 1/f spectral noise, and separately were decoupled from the attenuating impacts of reducing the duty cycle of our transmitter. Our mixer topology uses an OTA in feedback controlled by a clock signal to produce full +1, -1 mixing at the output using switching-based mixer techniques. Depending on the clock phase, the signal in the common mode will be presented into the OTA subcircuit such that either a standard inverting OTA amplifier or non-inverting OTA amplifier is seen, and the feedback resistors values are selected such that the magnitude of the output is the same regardless of the clock phase. However, the phase is either inverted to 180 degrees or left at 0 degrees. Since the clock signal being fed into the mixer is produced by the LED driver elsewhere on the chip, the received PPG signal is always synchronous here, which allows convenient downmixing and upmixing of our signals of interest and the surrounding noises and sources of interference. In effect, this allows us to perform noise shaping where the initial 1/f noise profile surrounding the signal of interest coming out of the TIA is removed, and a lower spectral noise copy of the signal is mixed down and fed into the filter stage. Though the general mixing technique leveraged here is passive in the sense that we're using switching techniques to achieve the desired mixing effects, we did use the values of the resistors used in feedback to produce a constant gain of 2x at the output of our mixer. This was intended to offset the losses in conversion gain of a switching mixer, and also to ensure that our noise factor wouldn't take too much of a hit having a low gain stage this early on in our signal chain. Ultimately, what we hoped to show is that the increase in noise introduced by this block would be overshadowed by the reduction in noise from our noise shaping behavior to ultimately improve SNR with this block, and this is shown in our results section later on. For our filter block, we used a cascade of two Mossberg-Ackerberg biquads configured as bandpass filters to achieve our desired signal processing. We understood that a native PPG signal includes both DC terms and low-frequency sources of interference that are typically a consequence of the user moving, in addition to a lot of high-frequency sources of interference and high-frequency spectral noise, and a cascade of two bandpass filters allowed us to achieve a sharp roll-off outside of our small, low-frequency desired passband. The Mossberg-Ackerberg bandpass topology is quite similar to a Towe-Thomas biquad, but changes the second integrator used in the loop. As with the standard bandpass Towe-Thomas, the signal first goes into a lossy integrator, and then this goes into a second non-inverting integrator subcircuit comprising of two OTAs in feedback. The output of this is in turn fed back into the summing node of the first lossy integrator, which produces the desired bandpass characteristic.
The programmable gain amplifier is implemented as two identical stages, with each stage consisting of an operational transconductance amplifier placed in an inverting gain topology. Each stage is implemented using switchable feedback resistors, allowing the gain to be controlled using digital off-chip signals. With two different feedback resistors, each stage can have 16.5 dB, 20 dB, or 26 dB of voltage gain. Plus, with two stages in series, we have a wide variety of voltage gains for the PGA. Tunability was essential here in order to minimize power consumption, as most of the power budget already went towards other blocks in the system, and being flexible with gain is important with our variable duty cycling, the whole point of our project, and to keep power consumption as low as possible. At the end of our signal chain is the lovely hysteresis comparator, serving as a 1-bit A to D converter for a digital output of our chip. Using internally cross-coupled transistors results in a positive feedback and hysteresis with a target of more than 100 millivolts. Hysteresis is implemented here in order to counteract any 1/f noise that gets amplified through our signal chain and shows up at the output. The comparator is the lowest power block in our system, consuming just 63 microwatts of power.
Due to pin limitations, a master current mirror was created to group together the reference current for a group of blocks. There are 4 current references, one for the LED driver, one for the TIAs, one for the filter and mixer, and one for the PGA and comparators. The master current mirror was sized to minimize the effect of channel in modulation, as well as have a small error in the mirroring current value from the reference current.
One of the key questions in the design of this chip was whether our high-frequency, more involved signal chain would be advantageous compared to the original baseline that we had planned to develop. Thus, a final step to our planning in the spring was to realize full signal-in, signal-out simulations of each of these blocks and to evaluate whether on some level the HF chain would benefit our SNR. Prior to conducting either of these tests, we first produced an ideal current model of a native PPG signal that's been duty cycled by 50%. The exact methodology as to how this was produced will be discussed in more detail on our website, but in general, this was used as a common input to both signal in and signal out tests. On the slide below, you can see our low-frequency chain and the basic operating principle being verified. You can see that we have this duty-cycled input going into the TIA in the current domain, the TIA outputs due to some low-pass filtering in the LF chain, the 1 Hz signal of interest, and some remaining interference at high frequencies. The filter takes this in, cleans it up, removes those high-frequency switching components fully, and provides some gain to the signal of interest, before the PGAs increase this to a sensible voltage domain, and then the comparator converts this to a 1-bit digital output, wherein the heart rate, or the fundamental frequency, is encoded in the rising edge of the square wave. On this next slide, you can see the time domain inputs and outputs to our mixer block and the HF chain at large. However, this is not particularly helpful in getting insights into the operation of this. On this next slide, you can see the frequency domain representation of what's happening in the DFTs of the input and output signals to our mixer block simulated over several seconds. The mixer output is shown in blue and the mixer input is shown in green, and what we can infer from this is that the mixer block reduces the DC components that are sent into it, reduces the surrounding 1/f noise that goes into it in the noise shaping behavior that it presents, and also increases the amplitude of the received signal of interest at 1 Hz. As you can see, that blue signal peaking up above there at the 1 Hz frequency. Ultimately, these simulations serve to give us confidence prior to tape out that our high-frequency chain would present some benefits in our signal processing and the overall sensitivity of our receiver chain. The question of whether our added power budget would make this improvement worthwhile was explored further in the fall.
Now, I will begin to talk about the physical design of our chip. This chip features 5 power domains represented by each color as shown by the figure on the right. The floor planning was optimized in order to keep the noisy driver of the LED driver away from the analog front end. Additionally, pins were allocated for input and outputs, as well as nodes where we knew we would like access to during testing. Here, in this image, I am showing you the layout without any of the top metals to show off each individual block more clearly. The LED driver is towards the bottom, away from most of the analog front end blocks in order to accomplish this noise isolation. Additionally, the master current mirror is in the middle for ease of routing, and most of the analog front end is towards the top of the chip, again to keep it away from the LED driver. Finally, here's a view of our final layout with the decap and routing to the ESD path. Additionally, on top of that, the chip art is on the top layer shown in white.
Our PCB was developed to meet 3 fundamental goals. Firstly, we wanted to be able to operate each of our signal processing blocks independently of one another. Second of all, we wanted to be able to manually dial in any control features on the board. And finally, we want to be able to output our final signal in human-readable terms on the same testing PCB as the rest of our chip and system. To accomplish that first point, an LDO in the bottom center of our PCB layout takes in some battery voltage and produces our desired 2.5 volt rail spread across the chip on the red layer seen in the attached PCB layout. This main power rail connects to the individual power domains of our chip via 5 hand-toggleable connections on the left side of the PCB, and these are next to all the current biases going into our chip, which are found on the bottom left of the circuit board. When it comes to making sure that everything was able to be dialed in by hand, all of our relevant reference signals and control signals were achieved using potentiometers that could be adjusted on the fly, or for our digital inputs, those were controlled via switches that we could change freely during testing. Though our final testing board seen elsewhere in this video includes more than just the original PCB, the whole system can function as designed in the full scope that we planned it for. We had what I'll call a medical accident with our original Arduino leading up to the day of our final demo, and had to replace it with another Arduino that did not fit the footprint kind of on the last minute. But on account of the design, it was fairly easy to extract the digital output of our chip from the board and port it over where it was needed. And this gave us an opportunity, or the motivation, to dust off our laser cutting skills and put in some last extra craftsmanship to the whole system going up to our final demo.
We would like to thank, first of all, our instructor, Dr. Peter Kingan, for advising us throughout this process and giving us a whole lot of healthy positive and negative feedback along the way.
We would like to thank our TA, Bert, as well as the other supporting TAs for the countless nights that they spent with us, helping to debug and fix our circuits that we were building.
We'd like to thank our fellow classmates for all their help academically, all the positive energy they brought for us.
You weren't that buggy. But last of all, second to last of all, we'd like to thank Richard Lee, the EE lab manager, and Joe Viola, the biomedical engineering lab manager, for loaning us a lot of stuff, in addition to giving us some helpful feedback at key points in our verification process.
Finally, we would like to thank our sponsor, Apple. None of this would have been possible without them, and we are grateful for your funding.
Thank you.
Thank you.
Thank you.